Okay, let's go ahead and get started. It is now 10 past, and so we're going to be doing a sort of one-off topic today because we're going to be talking about matrix sketching, which I normally teach with the sketching portion of the class, but I wanted to wait until some of you who are also taking MAT1840 finally learned about SVDs properly, so since that'll play a role in some of the proofs. So I guess first, let's recall that SVDs are one way of approximating a matrix. What do we mean by that? Well, you can just take the SVD, zero out all the smaller singular values, and then that gets you a low rank approximation of your original matrix. So our one way of approximating a matrix, so this is from MAT1840. But of course, in the sketching portion of our class, we also talked about a lot of other ways of doing approximations, and usually involving some kind of random sampling, often with a hash function, but some kind of random sampling-based method to approximate a matrix, or to approximate a function. And so we're going to show that you can apply these same sorts of techniques to matrices. So we're going to be talking about sampling for matrix products. It's going to be a bit of a throwback to an earlier portion of our class. We finished up the wavelet section, and we're going to be talking a little bit more about sketching today. And this is hopefully just going to be a self-contained one-day lecture. So let's go ahead and start with letting A be an m by n matrix. And B is going to be a n by p matrix. And what do we want to do? We want to approximate AB. Approximate AB, which is, of course, an m by p matrix. Now, there's a naive approach to this. What's the naive approach? And how long does it take? Yeah, so the naive approach is just actually multiply them, and that gets you pretty. So what do you do, especially if you have small matrices? So just matrix multiplication, and that's in O of m and p time naively. So you might be able to do it slightly faster with fancy new matrix multiplication algorithms like Strassen, but at least naively it's m and p time. Okay, but now let's talk about how we might want to do an approximation of this in ideally lower amounts of computational time. So let's let A, I'm going to be using MATLAB notation here, just so if you're familiar with it, basically, this is going to be all integers of A with a particular, where the second index is equal to K. So this is going to be the kth column of A, and we're going to let, well, let's say B, K dot dot be the kth row. Kth row of B. Okay, well then you can think about the matrix product as just a sum of outer products, right? So if you can think of AB as equal to the sum for K equal 1 to n of each of the columns of A times each of the rows of B. This is an outer product, so what we're getting here is just a very tall and thin vector times a long and wide vector. And of course, this gives you a matrix that's m by p when you take this outer product. And so this is one way of thinking about the matrix product. And when we phrase the matrix product as this sum from 1 to n of these outer products, well, one thing you might imagine is, well, maybe you can sample the matrix product by just sampling the sum. So we have n things that we're adding all together, and well, maybe we don't need to add all of them. Maybe you can only add some of them and then do some appropriate scaling. And that's basically going to be the key to today's methods, which is now that we've phrased matrix multiplication as an outer product, well, let's sample AB. So sample AB by taking components with some probability, let's say pk greater than 0. And this is going to be arbitrary for now. Oh, that was the wrong color. Well, this is arbitrary for now. And later we'll try to figure out what probabilities we ought to be using to sample them. So more precisely, we're going to let z be equal to k. So this is a random variable with the probability pk for k in the set from 0 to n minus 1. 1 to n, a random variable. And once we've defined this random variable z, well then of course we can define the sampled a matrix, which is also a random variable. So we're going to define the sampled matrix X, which is going to be 1 over PZ, a column of A, the Z column of A, the Z, column number Z of A. So I'm used to saying this in American English where it'd just be the Z, but I'm not actually sure what the TH with Z would be. You should tell me if you know. Anyway, and the Z's row of B. And this is, of course, a matrix random variable. So any particular instantiation of X is going to be a rank 1 matrix, but in expectation, it's going to be precisely AB. And let's show that. So then the entry-wise expectation is just the expectation of X is equal to the sum over K equal 1 to N of, well, the probability that Z is equal to K over 1 over PK times the kth column of A times the kth row of B. And of course, list cancellation is the reason that we scaled by list amount. So it precisely cancels out. So this is just the sum from K equal 1 to N of this outer product, which of course is precisely equal to the matrix product. Okay, so now we have some estimator whose expectation is the thing we want. But of course, so whenever you're dealing with these statistical estimators, one of the things you worry a lot about is the variance of your estimator. So it doesn't help you very much if in expectation it's correct, but it's usually very far off. So what we want to show is that it is usually close to its expectation by some definition of close. And so we're going to define an entry-wise variance, and that's how we're going to control the how far the deviation. So let's define the variance of X as just the expectation of AB minus X in the Frobenius norm squared. So this is the entry-wise variance. And of course, the Frobenius norm is just the squared sum of all the entries of a matrix. Then the variance of of X. Was there a chat? I thought I saw something. Oh no, there wasn't. Okay, so I'll have that upload. So then the variance of X is equal to, well, some double sum for I equal 1 to M and J equal 1 to P of the variance of Xij. This is by definition, so we're doing this as the entry-wise variance, which is equal to the sum over Ij of the expectation of Xij squared minus the expectation of Xij squared. And well, this thing is equal to, what we're going to do is we're going to break this out a little bit more. So sum over Ij, sum over K equal 1 to N of Pk times 1 over Pk squared times Aik squared Bkj squared minus, so that is this bit, right? So we're just taking the square of the Xij's and using the standard definition of expectation minus, well, look at what is the expectation of Xij? What is this expectation here? So this is actually when you when you take the summation. So you have that expectation and you sum over it. So if we're taking the sum and doing it all over both of them, that actually gets you the Frobenius norm of wait, did I write that down? Yes, Frobenius norm of AB squared. Because that is precisely equal to the sum over Ij of the expectation of Xij squared. Is that all right with everyone so far? Oh, okay. So what we were doing is we're defining this thing as the entry-wise this expectation, right? So when we did this, the first thing we did is, since it's the entry-wise variance, we broke it up into all of the pieces. So the variance of x is the summed variance of all the individual entries of x. Oh, wait, did I write this down? No, oh, then, okay, I think I see the confusion, which is if you look at this thing, the Frobenius norm of AB minus x squared, that's precisely the sum over ij of AB sub ij minus xij squared, right? And so that's what we're using here. So basically, we're using the Frobenius norm squared as just the squared sum of all the entries. Okay. So now, what do we want to do? We want to minimize this variance, right? So we have some definition of variance and we want to minimize it. So we want to choose pk to minimize the variance. And this sort of explains why we broke it up in this way, because this thing doesn't matter. Doesn't matter for minimization. Right, because there's no term of pk in there. So like there are no pk's in there, that just happens to be the Frobenius norm. And so whatever it is, it will play a role in the variance, but you can't minimize it. Like it's just effectively a constant term as far as the pk's are concerned. So, well, let's see what happens when we take this variance and when we take this part of the variance. So let's just take that part and try to minimize that. Well, let's see what we get when we expand it out a little bit. So this is just the sum over ij, the sum over k, pk times 1 over pk squared, aik squared. I'm totally going to mess up these indices at some point, bkj squared. So that's equal to the sum. Well, now we're going to use our standard trick of just moving around all the indices and the summations. And so we're going to have the sum on the outside be the sum over k of 1 over pk. And then we're going to have a sum over I of aik squared and a sum over j of bkj squared. And so you notice that we can separate it out in this way. And so then this is just the sum over k of 1 over pk. And what is this term here? Yeah, so this is just the kth column, the norm of lat squared. So the 2 norm of lat squared. And this is going to be b, the kth row of b. And the 2 norm of lat, the Euclidean norm of lat squared. So here, these are Euclidean norms. So Euclidean norms. And this starts getting at how we ought to be doing the sampling, right? So we know that this thing is the variance is basically determined by the squared Euclidean norm. So it's determined by the squared lengths of each of the columns and rows thought of as, well, vectors in your high dimensional space. And now we want to minimize this. And luckily, that's something we can do. So those of you who are taking 1850, we'll have seen a little bit of optimization, but we're only going to be using quite baby optimization, and we're not going to be doing anything super fancy. So it's just going to go back to multivariable calculus and how you optimize for extrema. So let's say we have a function f of p1 through pk. That's equal to some sum over k equal 1 to n of some ck over pk, where we know that our ck's are greater than or equal to 0, and pk is greater than 0. Okay, so this is the general form of the problem we have. When subject to the condition that the sum of all the p1s through pk is equal to 1, then the minimum of f is achieved by pk is proportional to root of ck. Okay, so the statement is just basically, this is, in order to minimize this function f, you need to have each of your pk values to be proportional to your the root of each of these ck values. And we'll apply this in a moment, and we'll see that basically that tells us how we ought to choose our probabilities. Excuse me, sorry. So let's prove this. Does anyone have any ideas how we ought to begin this proof? So you could do that, but it turns out we don't need anything so fancy. This is actually much easier than that. So without loss of generality, we can say that C1 is greater than 0, right? So clearly one of our CKs must be greater than 0, because if they're all equal to 0, then, well, there's no point in like talking about this. So without loss of generality, say that C1 is greater than 0. And then we're going to remove P1 by just using this equation. And so instead of having a constrained optimization, we're going to turn this into an unconstrained optimization, since those are easy. So then we'll set some, this is really some F tilde, but I'm just going to call it F to make life easier. So F of P2 through Pn is going to be equal to, well, plug that in. So it's going to be C1 over 1 minus P2 through Pn, the sum of that, plus the sum over K equal 2 to N of Ck over Pk. So note that this is now we have an unconstrained optimization. And that should be easy. So how do we do an unconstrained optimization? We just take derivatives, right? So let's see what it is if we take the kth derivative. So the derivative with respect to the variable pk. So then what we're going to get is we're going to get partial f partial pk is going to be equal to, well, you're going to have c1 over 1 minus p2 plus dot dot plus pn squared, because there's a minus pk entry somewhere in there. And so when you take the derivative, you get a negative sign out of that, but you also get a negative sign out of the minus fact that's in the denominator, and so those cancel out. And similarly, you get a minus pk over pk squared, right? And we know this is equal to 0 because we're trying to find an extrema. And this is going to imply that pk over 1 minus p2 dot 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 plus through pn is equal to the square root of ck divided by c1. And this is why we had to have c1 be not equal to 0, which of course implies that pk is equal to root ck times 1 minus p2 through pn divided by root c1 for all k not equal to 1. So all the pk's not equal to 1 are proportional to root ck. But of course, 1 was not chosen in any sort of special way, and therefore this is true for all of your entries, and that completes the proof. I mean, I'm sort of like this only proves that that is a minimum or maximum. You can check that it's actually the minimum, but we're not going to do that in this class. We're not going to bother. So, well, what do we know from that? So from that lemma, plus we know that we want to pick our pk to be proportional to the length of the kth column times the length of the kth row of B. And so this gives us, for our sampling method, this gives us the probabilities we ought to be selecting each row, which is we ought to select a row column pair. Sorry, column row pair. I don't know which way you're looking, but a row column pair such that the product of their lengths is proportional to the probability of you're selecting them. And well, so this tells us the best thing we can do. Is this good enough? So like, is this sampling approximation, is the variance of this good enough for practical use? And that's not necessarily clear, but let's try to analyze it in a simpler case, and I'll give us some more information about what we ought to be doing. So, well, let's just start by noting there's a very simple case. When B is equal to A transpose, then that just means that PK is proportional to the squared length. So this is just squared length of column. And note that if you were to make this choice, it would be worse than the choice we have above, right? So if you were to choose your PK to be this thing, then it's worse than that thing, right? As far as variance goes. Because we know that this is the minimum variance. And so any other choice can only be worse, right? I mean, it might be the same, but it certainly won't be better. But because it won't be better, so that means that even if B is not equal to A transpose, we can still use this as an upper bound. Use as easy to analyze upper bound. Okay, because like we know what the optimal value is, we're not choosing the optimal value, so clearly we're getting an upper bound on whatever the variance where we get is. So we're going to use pk is equal to the kth column of A that length squared divided by the Frobenius norm of A. Because of course the sum of all of your squared lengths is exactly your Frobenius norm. Okay, and this implies, well, this makes the computing the expectation a lot easier. So actually, it didn't really matter if we chose it to be, we could have also chosen lat squared, and we'll get the same thing, but we'll see that in a moment. And this is just the upper bound. So, well, what's the expectation of AB minus X Frobenius norm squared? I mean, this is just what we define as the variance of X. This is less than or equal to the Frobenius norm of, oh, so where is my formula? So I think my formula was here, right? So now all we have to do is you have to plug in this value of pk. But note that when you plug in this value of pk, you end up, that's 1 over pk, so you end up with Frobenius norm squared here, and times the squared lengths precisely cancel out. And that's by design. So those lengths precisely cancel out. And so then you just get the sum over k of the squared length of all the rows of k. And this is just the Frobenius norm of A squared times the Frobenius norm of B squared. Okay, so this gives you an upper bound on the variance. Clearly, we might be doing better when we choose the optimal value. But certainly, even if we choose this not optimal value, we have an upper bound that's just the squared Frobenius norms of both matrices squared. And now that we know an upper bound on the variance, well, we can use our standard trick of just doing this many times. So if you think about it, right now our random variable x is just taking a single row and column and sampling as your sample, and then saying, well, that's about your original matrix. And that's not quite true. But if you do this many times, you can actually bring down the variance. And so that's the standard thing we're going to do. We're going to repeat an average. So repeat with S independent trials. So then we get a bunch of random variables, x1 through xs. And well, then we know that the variance of x bar, so just the average of all these random variables, is equal to 1 over s times the sum from I equal 1 to s of the variance of xi, which is just equal to 1 over s. Just a moment, I think I did something wrong there. Yeah, so anyway, because it's a sum over all those, the variance decreases with the number of times you try it. So you end up getting 1 over s times the variance of x, which is of course less than or equal to 1 over s times the 2 Frobenius norms squared. So now what are we doing when we're doing these S independent trials? Basically what you're doing is you're taking S different, well, not necessarily different since you're drawing with replacement, but you can think of it as taking S different columns of A and S and the corresponding S rows of B, and using that as a sample of your entire matrix. So you're basically subsampling some particular set of rows of the columns of A and rows of B, and that gets you something relatively close to your original matrix. So when we draw this out, that looks something like, we have A, which is an m by n matrix, and we have, say, B, which is an n by p matrix. And that's approximately, I don't know if those dimensions look right, but that's approximately equal to some other thing, C, which is scaled sampled columns of A, times the corresponding scaled rows of B. So we're going to call this matrix here, well, we're going to give them names in a moment. But anyway, so writing this out a little bit more formally, this is 1 over s times the sum over I equal 1 to s of xi is just 1 over s times, well, each of these different samples. So A, the k1th column of A times the k1th row of B, divided by the probability of choosing that, and so on for all s of these things. Sorry, there are so many little dots to write down when I'm using this notation. It's a notation that really makes more sense on the computer than it does when writing by hand, because I have to put in so many dots. P sub ks. And we're going to call this matrix C, and we're going to call this matrix R. So this is equal to CR. Because basically, you're just taking each of these columns after some scaling, and so on. Where the scaling is, of course, this probability related to that. Yeah. Well, what is C? C has columns. C has columns which are a ki divided by root spki, and R has rows which are b ki divided by root spki. And just as an important note, one thing that you may have noticed is that the expectation of CC transpose is equal to AA transpose, and the expectation of R transpose R is equal to B transpose B. Okay, and then that's something you can double check. It's straightforward. It's the same way we found that the expectation of the overall thing is the matrix AB. So what is the punchline of all this? The punchline of all this is that we do, like, in this sort of matrix sampling, when you do it multiple times, that's basically just taking the original matrix, taking some subset of the columns out of it, scaling them appropriately based on their scaled length, and then multiplying it by doing the same scaling on the other matrix B. And this brings us to, well, we've basically done all the steps of proving this theorem, but let's write it all down as a theorem. Theorem 6.5 in your textbook. So suppose that, well, we have the same setup, and B is a n by P matrix. Then AB can be estimated by CR above, and the error is bounded. Error is bounded by the expectation of AB minus CR, the Frobenius norm of that expectation, squared, is less than or equal to the Frobenius norms of our original matrices, squared divided by S. And to ensure that we get something reasonable, so to ensure that this is, to ensure that's less than or equal to epsilon squared, it suffices to choose S greater than or equal to 1 over epsilon squared. Which implies that CR can be computed in O of 1 over epsilon squared MP plus MN plus NP time. Where are all these pieces from? Well, this is actually computing CR. And this one here is just sampling columns of A. And this one here is sampling rows of B. By which I mean we need to actually measure their lengths. And so you can't get away from like reading those matrices. But this is what we get. And this is if 1 over epsilon squared isn't too big, or if S isn't too big, then this is more efficient than just taking the matrix product itself. If S is big, well, then maybe this doesn't work so well. But now that is the question, of course. When is this a good estimate? And this is kind of hard because we have all these different things at play. So let's consider a simpler case. Let's actually just consider the simple case that we've been using for our proofs, which is let's consider the case where B is equal to A transpose. B is equal to A transpose for simplicity. Because that's easy to analyze since we know how to deal with A transpose. So, well, then let's consider the simplest possible non-trivial matrix. What is that? Yeah, it's a diagonal matrix. In fact, the simplest possible diagonal matrix is just the identity matrix. So let's say that A is equal to the identity matrix. So what's the Frobenius norm of I transpose squared? Where the dimension is n, let's say. And this value will just be n. So that's easy enough, right? You just take all the entries, which are only on the diagonal, and they're all 1. You square them, they're still 1. You add them up, you get n, you square it, and then you, you take the square root, and then you square there, etc. And you get n, but we know that our bound here, that's equal to n squared over s. Okay, so this is actually not so good for us. So because then we need s to be greater than n for bound to be useful. Right? Because if n is less than that, then you're not actually doing better. So this is bad. And why is this bad? This is because you can always just do the trivial estimate. So trivial estimate of the zero matrix. So you can always estimate a product is 0, and then at most you're off by the Frobenius norm of the product by definition. So the trivial estimate of the zero matrix gives error A transpose F squared. So we need to be at least as good. Because if you're not as good as the zero estimate, then you really have no business like estimating it. And in this particular case for the identity matrix, our method needs more than n samples for it to be as good as the zero estimate. So this is no good. And so the sort of intuition that we're getting at here is that if your original matrix is highly diffuse, in the sense that you have, and we'll define this in terms of the SVD, but in terms of if you have all the mass that's spread out across all the different eigenvectors, then the sampling does not work very well. Because then you may as well just like take all the different, take all of them. So if you have this uniform distribution, and where we'll see that, where we'll see in a little bit that where we shine though, is when most of that mass is concentrated in a few singular values. And if that's the case, then our sampling method will be better. And that sort of makes sense, right? Because if you think about an SVD as a low rank approximation, well, if all the singular values of your matrix are equal, then doing a rank k approximation is actually not very good, because no matter what you choose, you're going to be losing out on a significant fraction of the mass. And so this is what's going to inform our analysis. We're going to do an analysis via the SVD. And this is why I waited until you guys had taken SVDs in MAT1850. So so let's ask you a simple question. When is the SVD approximation good? And recall that the SVD is just A is equal to U sigma V transpose, where U and V transpose are orthogonal matrices, and sigma is a diagonal matrix. Well, the answer to this is when the top P singular values take up a large constant fraction of Frobenius mass. Right, so one thing that's important to recall is, of course, and this is very easy to prove once you, is that the Frobenius norm of F squared is just equal to sigma 1 squared plus dot 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 plus sigma R squared, where R is equal to the rank of A. And each of these sigmas are form the diagonal matrix. Right, and you can sort of see this because orthogonal matrices don't actually change anything, and so you don't have to worry about them changing the mass of a matrix. Okay, I feel like I'm going really fast. Is everyone still all right? Okay, great. So let's keep on going. So now let's suppose that there exists some C greater than 0 and less than 1, and a small integer p, such that for a matrix A, sigma 1 squared plus dot 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 plus sigma p squared is greater than or equal to C times sigma 1 squared through sigma R squared. Okay, so basically what we're saying is that the first P singular values take up mass, fraction C. So C is some fraction. And we want this to be a relatively big fraction, but the first P singular vectors values take up a p fraction of the, a c fraction of the Frobenius mass. And of course, note that a transpose, that Frobenius norm squared, is of course just equal to at least all your singular values to the fourth power. And just to repeat again, Frobenius norm of just a matrix is all the singular values squared summed. Okay, so that's exactly what we wrote up here. So then we know that, I can't write with an eraser. Then we know that the expectation of A transpose minus CR F Frobenius norm squared is less than or equal to this. So this is just our original statement. And that, come back. That is equivalent to, okay, and what do we want? We want the approximation to be good. So for approx to be good, we want that the Frobenius norm of A, so this thing here, divided by S, is less than or equal to the Frobenius norm of A transpose F squared. Because that's the error of the zero approximation. So we want it to be at least this good. Well, we can rewrite this in terms of the singular values, which is the entire reason we started with that. So sigma 1 squared plus dot 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 plus sigma r squared has to be less than or equal to S times sigma 1 to the fourth plus dot 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 plus sigma r to the fourth, right? And that implies that S has to be greater than or equal to sigma 1 squared plus dot 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 plus sigma r squared divided by the sum of just the fourth powers of all these singular values. But now note that this could be bad in the general case. Note that the max over sigma 1 through sigma r. So for a general matrix with any possible singular values, this thing is equal to R. Because you could, and this corresponds precisely to the case that we talked about earlier with the identity, where if the mass is evenly distributed, if all your sigmas are equal to 1, you get precisely R. So this is not a good bound. So not good bound. But we have the additional assumption we made up here that these things, these things are a constant fraction. And so we can use that back. So, but we know that sigma 1 squared plus sigma r squared over sigma 1 to the fourth plus plus sigma r to the fourth. Well, that's less than or equal to sigma 1 squared plus sigma p squared over c squared times sigma 1 to the fourth plus sigma r to the fourth, which is less than or equal to sigma 1 squared plus sigma p squared times over c squared times, did I mean c squared or did I mean c there? No, I did mean c squared. Okay. Sigma 1 to the fourth plus sigma p to the fourth. Why is that? Because if you make the denominator smaller, then clearly you're just making the fraction bigger. And this is less than or equal to p over c squared. Plus, if s is greater than or equal to p over c squared, then the approximation is better than zero matrix. Okay, so basically, if your SVD approximation would be good, so if your rank K SVD approximation would be good, then this approximation also tends to be better. So basically, the sort of intuition is that if the mass is concentrated in a few singular vectors, then with high likelihood, when you sample a random column based on its weight, then you're probably getting at whatever singular vector that was. So you're getting at some of that mass because, and therefore with high probability, you don't, because you're sampling according to that, you have a high probability of getting the big singular vectors. And so therefore, our CR approximation is sort of close to what you would have gotten if you had done an actual SVD. But an actual SVD is a bit more expensive. And so here, this allows us to just sample and do something that's works in the same setting that the SVD does, costs less, but isn't quite as good of an approximation. Okay, do I have time? I have 10 minutes, so let's see if we can do this. So That was, of course, just sampling the product of two matrices. One thing you might also want to do is sample just a single matrix. So, and it turns out we can do that. And the way you do that list is basically based on the sort of sampling these products. And we'll see that in a moment. So if A is in R to the m by n, let's say it's a data matrix. So if it's a data matrix, you have a bunch of samples and you have a bunch of features, right? So one example I like to use is expression of mRNA, because I'm a computational biologist and I like things like mRNA. But really, you can think of this as any set of samples and any set of numerical features. So this obviously doesn't work for well, I mean, not obviously, but it's not as obvious what this means when you're dealing with categorical features. But if you have numerical features like the amount of expression of something, or like a height or an age or some number like that, well, you might consider taking a low dimensional representation of this by doing an SVD, right? So may want low dimensional representation. And the SVD A equal U sigma V transpose is a natural solution. But this takes O of mn times the minimum of m and n time, which is about O of n cubed. Okay, so assuming that n is about equal to m. But there are also a couple of other issues with using the SVD. So the SVD does give you a low dimensional embedding, and this is used in things like PCA, which you may have heard of. But this destroys any sparsity that was in the original vectors, because each of your SVD, your singular vectors, is some mix of all the columns of your original matrix, right? And it's also not very interpretable because you get some mix of samples. And so, like, what actually is your first principal component? Like, what does that mean? And that's not always obvious from looking at the things. On the other hand, if you were doing a sketching by sampling columns, it has a much more natural interpretation, because you can be like, oh, well, that whatever column I used as the sample, well, we can look at that particular column, and well, that is precisely one of the features of that we're looking at. And so what we're going to basically do is we're going to do sketching by sampling columns in that way. And this will have some nice interpretability and also will be computationally quicker. I think I am speeding up with my speech. So let me try to slow that down a little bit. So this is theorem 6.9 in the textbook. And we're not going to fully prove this, so we're going to run out of time. But if you're interested, this is in your textbook, and there's a ton of matrix sketching literature. But I'm just going to try to give you a flavor of what's going on here, since I don't want to spend too much of our class on this. So let's suppose that we have some m by n matrix, and the two values R and S that are positive integers. Well, we're going to let C be a m by S matrix of S columns of a picked via linked square sampling. And we're going to let R, which is going to be an R by N matrix of R rows of a picked via linked square sampling. Then the statement of the theorem is we can find from C and R a new matrix U in which is an S by R matrix, such that the expectation of, we're going to be using the 2 norm here, but A minus CUR, the 2 norm squared, is less than or equal to the Frobenius norm of A squared times 2 over root R plus 2R over S. Okay, and yes, we're not actually going to take the time to derive all the different pieces, but the basic idea here is you might be, the basic idea here is that we can come up with some approximation of this matrix whose 2 norm is not that different from the 2 norm of the original matrix. So if we fix X, so let's just go ahead and finish this theorem. So if we fix S, well, we can minimize the error. Minimize error with R is equal to S to the 2/3. And we can choose S is equal to 1 over epsilon cubed, and R is equal to 1 over epsilon squared. Well, then we know that the expectation, in that case, would be with those choices, we get that the error squared is approximately O of epsilon times the Frobenius norm of A. Okay, so with this choice, you can come up with some little dimensional like representation of your big matrix A, whose norm is not that far off, whose norm is not that far off, as measured by the Frobenius norm. And just to compare, let's recall that A minus AK, where this is the best rank K approximation via the SVD. Well, this thing is just equal to sigma K plus 1 squared, which is less than or equal to sigma 1 squared plus blah, 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 plus sigma K squared over K, which is less than or equal to the Frobenius norm of F squared over K. And so it has a similar form. So basically, what we can say is that we have a similar form of error, but it's not quite as good as if we were to use the SVD. So it's basically the same story as we were telling a moment ago. And I am not going to have time to even like give you a flavor of the proof, am I? Well, let's keep on going and see how far I get. So the basic idea here is that we have some matrix A, which is n by m, and that's going to be equal to some set of sampled columns. This is n by s, times some multiplier matrix, which is s by r, times sampled rows, r by m, and these are our C, U, and R matrices. So this is sort of like the SVD where we had a U, sigma, and D transpose matrix, except that the middle matrix here is not diagonal. But we still have sampled columns, but instead of having these singular vectors, we have these sampled columns and sampled rows instead. How much of this can I show? I think that it would do a disservice for me to actually try to do all this. If you are interested in this, I do have more of the notes on the online version of the notes, and this is in your textbook in more gory detail. But this is basically you make use of matrix multiplication with a projection matrix. So we have this property of matrix sampling for matrix multiplication, and you also know something about projection matrices. So if you do something like the Moore Penrose pseudo inverse, that ends up being some kind of projection matrix. And then with the projection, and then when you take a matrix times a projection matrix, that's a matrix multiplication. And then you can apply your matrix multiplication sampling to basically prove this matrix sketching theorem. And with that, I will end for today. Does anyone have any questions? Thank you very much then.